Hi, in this tutorial I'm gonna talk about the Kalman filter, but before I start this tutorial, I strongly recommend you to have a look on my other video about the beige filter, because all these filters, Kalman filter, particle filter, extended Kalman filter, unscented Kalman filter, they all have the same root in the beige filter. They all have these two steps of prediction and update, which you have a model. Based on your model, you predict the best estimate of your belief, and then you go into the new state. You do some measurements, and according to your measurements, you get another belief, and now you have to fuse these two beliefs to get a better estimate of your state. So you have your two-state prediction and update, and you use total probability and Bayes rule in these two steps. So they are very similar, but they have different assumptions, like single hypothesis, multiple hypothesis, linear model, nonlinear model. Here in Kalman filter we have linear. We have the assumption of single hypothesis, means that we have only one hypothesis for our state, one Gaussian, and it's linear. It means the relation between two states, xk and xk plus 1 or minus 1, is linear and could be defined in the form of a matrix. Also, the noise over our noise over our sensor is also Gaussian, and we have a mean, and we model the uncertainty about the sensor or the model with our covariance or variance. Okay, these are the assumptions for the Kalman filter, and now I'm gonna go through some intro, some math, and then I'll start the equation. I'm gonna drive the equation. I'm gonna walk through them. Okay, so very simple. 1D case of normal distribution or Gaussian distribution is you have a mean, and the general shape is something like this. You have a mean, and how much uncertainty you have about your state is defined by a variance. So if it is a big number, it's gonna be heat is gonna be wider, and if it's a smaller, it's gonna be it's gonna shrink. And in general case of n-dimensional, this mu gonna be a vector, and we're gonna have a covariance, which is a matrix of n by n. Okay, some properties. What would happen if you multiply every point in your normal distribution, your Gaussian distribution, by a fixed number k? So if I multiply it by k, and this is a previous marker. So if this is my first one, and I multiply it by k, the second one gonna be k times mu, and it's pretty intuitive. If you have a couple of numbers like 1, 2, 3, the average is 2. If you multiply by 2, then you have 2, 4, 6, and the average is now 4. So the new mean gonna be k times multiplied by old mean. And as you can see in our simple example 1, 2, 3, you can see the variance is going to be bigger, so we have more uncertainty, and the new variance going to be k squared, the old one. And in the case of n-dimensional, if you multiply every point by a matrix, for instance, called F, then your new mean vector gonna be F time your old one, and your new covariance gonna be F time previous covariance multiplied by F transpose. So these are the, some properties that you have to know before we continue. The other thing is that we have to know is that when you have how to fuse our data. Okay, let's say you have belief about some state. For instance, you know that your robot is located on a specific position, and you have some beliefs about that, and you model with some Gaussian distribution. So you have something like this. Okay, so you will do a measurement and you will have another belief. So now you have two state estimation, and somehow you trust both of them, and you want to fuse these two to get a better estimate. So to be both of them to be true, it's a joint probability. So if both of them gonna be true, then it's gonna be multiplication of the probability. So if you have one beliefs, which is something like this, and this is mu 0, and another one which is something like this, then you're probably here. So this could be two different measurements, or this could be something coming from your model and the other one coming from your measurements. Anyhow, so we multiply these two Gaussian, and you know when you multiply two Gaussian, you still have the result is a Gaussian. And you have to remember that these are actually probability distribution function. These are not probability. Any point on this doesn't make any sense. Only integral over a specific period like A and B is something meaningful, and it's a probability. So the chance of being between A, for instance, this point and this point is a probability. And when you multiply this and the integral over all this Gaussian over minus infinity to the infinity, this should be 1. So when you multiply these two, in order to have a still valid probability distribution function, we have to normalize it. So it's stay okay. The result is Gaussian, but we have to normalize it to be a valid PDF function. Okay, if you do this, do some formula and Twain-Gromit formula, you can retrieve the new mean and new covariance based on these two, which I'm gonna write it down for you here. It's gonna be the new mean gonna be the old mean plus power 2 mu 0 or and the variance is going to be okay. So this part is pretty simple. Now if you massage this formula a little bit, you can rewrite it in this form. You can write it in the form following. So you can extract something called K, and the new mean. I'm just writing the formula from the previous page. I'm not doing anything special. This is not a new formula. Okay, so here here we have some interesting properties. Let's say the uncertainty about the first Gaussian is too much. Means this is a huge number, and when this is a huge number, the limits when it goes to infinity, it's gonna be 1. So the k goes to 1. When k is 1. These two terms gonna cancel out each other, so we only have mu1. So the new mean is gonna be the mu1, and it's the same for the variance. So, and it perfectly makes sense when one of your sources you don't have much trust on that. When the uncertainty is a really huge number, then the result of fusing these two data is closer to the other one. And let's say now this guy goes to infinity. It means we have uncertainty about this the second data. It could be again not necessarily from the measurement, could be anything, but let's say this goes to infinity, so this k goes to 0. Okay, and when k is 0, we can see the new mean is the mean 0, and this is pretty this is the essence of the Kalman filter, that this gain will tell us how much we get closer to our measurements or the model. And so the limits for k are 0 and 1, and let's write it down for the general form of n-dimensional case. So if it's 1D, if it's n-dimensional, so the k gonna be and the new mean gonna be and the new covariance gonna be okay. So this is equation number 1, equation number 2, and equation number 3. We're gonna need them soon. Okay, with this intro, we are ready to officially talk about the Kalman filter. So as I said, we have two-step prediction and update, and we use the total probability law and Bayes rule to do the correction. Okay, let us start with the state space. So what is a state space? Basically, it's the state that we like to estimate. This is arbitrary and this is changed for every problem. This is something that the problem that we try to solve dictate us. But let's say we're an easy case. We interested to track the position and velocity of a robot. So I have P and position and velocity, and okay, if these two parameters are not related, let me just write down the state. So and this is my covariance matrix. And as you can see, this matrix is symmetric. You can see, so it's equal to its transpose. And if these two parameters are not related to each other, means if position nothing to do with the velocity, if there's no correlation between them, it's going to be a Gaussian like this. But if there's a correlation between them, means these two elements are non-zero, then it's gonna be something like this, for instance, depending on the values here. Okay, now we know from the physics that if we are moving with a constant velocity and we are not exerting any force to our system, we can predict the new position based on the previous position, like this. Okay, so this P actually refers to the, okay, so sorry for bad notation. Actually, this P is the position here, and the velocity gonna be the same constant. So I can write it down. I can write it down this in the form of a matrix. So I will have xk. Okay, so as you can see here, I'm somehow relating my new state to the previous state, and this is if you remember from the first slide here, when you multiply this formula, when you multiply every element of an Gaussian distribution by a matrix, then the new mean and the new covariance are like this. Okay, so the I call this F, so my new state is so I'm predicting my if I'm following this model. This is my model. This is the called linear dynamical model. As you can see here, it's retrieved from this formula, which tells us the new position. It's perfect, makes sense. If the velocity is fixed, velocity multiplied by time plus previous position give us a new position, and the velocity is fixed. So what is the new covariance? Previous covariance multiplied by F multiple F transpose. So these are the new mean and covariance. So this is the estimate that our model will gives us for a new state. Now, in some cases, actually, we might exert some force to our system, which if you exert some force, it will cause some acceleration and the velocity gonna change. So I will write it down if we are exerting some force. So the new state gonna be the previous one plus. This is again come from physics that the new position gonna be the previous position plus acceleration multiplied by time square. So again, if I write it down in the form of matrix, so this is my Fk. Or I can again write it like this. Okay, so this is this guy called control vector, and this is a control matrix. This is a place that you send your motion commands and you make some changes in your system. So what's gonna be the covariance? We have the mean now. What is going to be the covariance, new covariance? Well, the new covariance, if we apply some forces, gonna be, because again, we have some uncertainty about that and we model it with the Gaussian, so we just add the we're just gonna model it with some covariance matrices. This is a covariance matrix. This is the uncertainty that we had comes from the force that we apply. So this is the best estimate of our state according to the model that we followed. That it was linear, and so this guy will tell us the mean, and this guy will tell us the covariance. So how much we this guy will tell us where is the parameter, where are the mean, and this guy will tell us how much uncertainty we have about that. Okay, so that was a prediction. Now let's go to update. Well, in the updated state, we let me just write it down. Correction or update. We will go to new state and we read the sensory data from our sensors. For example, read the plot position and velocity. And now we have one state that tells us the position and velocity from a model, and the other one is coming from a sensor. Now we have to, based on uncertainty that we have, which is this covariance matrix, we have to make a decision what is our actual state. But before continuing, because we might use different scales and unit in our sensor and our model, so we need to adjust them. For instance, we might use, I don't know, millimeter per second, meter per second, or something like this. So I will multiply our data by HK, this for unit scaling and taking care of physics stuff. And you know that if you multiply by a matrix, your new covariance gonna be HK, PK, HK transpose. Okay, now your sensory data will give you ZK, which are the means, and the RK, which is the covariance matrix. Okay, I'll just call them yes, and I'll call this mu0 and rs1. Sorry, 0. Okay, now let's put everything together. So we have one Gaussian, one state estimation with this form, with this mean and covariance, and we have our measurement data with following mean and covariance. Okay, if you remember from the first slide, because we trust both of them and we want to make a judgment based both of them, these are we just multiply them because it's a joint probability. So if I use the equation number 2, this equation I can go back to that to write down the new mean. I can put it here. Okay, so the new mean gonna be okay. So according to equation 2, let's write down that. This is not equation 2, but this is according to equation number 2. And equation number 3 for covariance. And equation number 1, which gives us the k. Okay, if you look carefully, I wrote it down in a way that I could have a hk in all of these equations, and I can just transpose multiple by inverse and or pseudo inverse to get rid of this hk. So this is just massaging the formula. This is not a new formula. So basically the most important was this part, which was based on the multiplication and retrieving these terms. So this will give me this means that we just remove this hk from the k, because if you have a look at the previous page, we already had a hk inside, so just wanted to distinguish that. Okay, so after fusing these two data, And according to the Kalman gain that we said, this is the best state estimation according to the sensory data and the model, and this is the new covariance. So depending on what we set there, will be biased toward measurement or the model. The other thing I'd like to tell you is all these linear transition model that we wrote down, and the covariance for the sensors or for the model, they all could be fixed, or they could change for every iteration. So it's again up to you. So the noise on the sensor might be fixed, or it might decrease or increase. And also about it's the same for our state model, and it's up to you. Okay, that was more or less everything, and have a good day.